guess who I am. Welcome to another Zephyr Tech Talk. Super happy to be back. So yeah, spoiler alert, today I'm actually going to be the one presenting, but I hope that, I'm sure I will do that again in the future, but usually I'd like you guys to be, and you folks to be on the show. So looking forward to have many of you back in the new year. I think we're nearing the end of the year, so we might it's probably one of the last episodes of the season, one would say. But yeah, we're going to talk about all things AI, artificial nose. But before that, and just as the motto, this is kind of the motto that we have. I would like everyone that just joined on YouTube, on LinkedIn, to just say hi from wherever they are from. And well, Charles, I think you are actually a regular, because you already know that I was going to ask that. So we have other people saying hi. Actually, we have Kate just saying hi from Austin, Texas, and Kate is actually the co-host today. Hello, Kate. Kate is my colleague, my boss, and yeah, just to make sure that we have some kind of a live discussion. There's going to be, of course, you all in the chat, but Katie is also going to be here to grill me with questions about all things artificial nose. And hello, yes, hello, Maciej from Poland. Hello, Oliver. Great to have you all. Yeah. So, I don't know, Kate, did you want to say a few words about yourself maybe before we kick it off?
Oh, no, I don't. Like I say, I'm just here to help facilitate this and be able, so Benjamin can basically do the demo, and I can keep an eye on what's going on with the chat and ask some questions. And so please, for people, as we start going through this, please ask questions, and we can try to have a good discussion going. That's the hope here today. And I'm certainly been excited. Like I say, I was not able to go to All Things Open and see Benjamin's talk, so I was very sad about it. Therefore, I'm looking forward to seeing the demo here now myself. Oh, Paris. Okay, France. Excellent. Toulouse. Oh, Munich. Excellent. Oh, hey, Samantha. Okay, yeah, I'm seeing some faces I know and some names I know. This is cool. Lisbon. Okay. Well, Benjamin, do you want to maybe start as this is going in?
Yes, I had just switched mic. Can you hear me?
Yes, we can.
Cool. Okay, because apparently I was on the wrong mic before. So yes, let's just get started. Hello, Briggs. Hello, wherever that is. Well, yeah, thanks everyone for joining. So as a way to kick the discussion, maybe some background for those who don't know about the project. You may have heard about it before. It was like early in the pandemic where I basically needed an excuse to learn myself some artificial intelligence, more specifically TinyML. Like the thing is, I'm a software engineer, but one thing that I really didn't get until only a few years ago, I guess, is how, like, what the heck neural networks are, and like understanding the way it works. Like I would open a book and try and understand, like those basic samples where you do like handwritten digit recognition. Supposedly it's like the 101 of artificial intelligence, and it's only a handful of pixels that you're trying to make sense of. But yeah, it just didn't work for me. But I had this idea right during the pandemic where I was like, okay, I'm French. Sure, I do like my bread. I do like I've been trying to perfect my bread recipe for many, many years. And I was thinking that maybe I could build some kind of device that would help me figure out when my sourdough starter would be perfectly fermented. And I've been playing with Arduinos and the like for many, many years. And I knew that gas sensors existed. And so there would be probably a way to measure the concentration of the things that probably matter to the fermentation of sourdough, like volatile organic compounds and CO2 and whatever else. Only like I didn't want to do the tweaking of whatever algorithm by hand. Ideally, I could use artificial intelligence to figure out, hey, you know what, I'm going to prepare my sourdough starter by eye, figure out that it looks kind of okay, and then bake the bread. And if the bread turns out good, then maybe I could label some kind of data sets and do some kind of training. So that's kind of how I started. And quickly, basically, I experimented with gas sensors that I had laying around, and try to fit the data into a neural network. And one thing that I basically did back then, and I will still have today as part of the demo and the walkthrough, is so I used TensorFlow Lite for microcontrollers, and we will touch a bit about what that is during the demo. And I used something called Edge Impulse, which is essentially a web IDE to oversimplify, that really helped me with the training of the data set, and figuring out essentially how to clean up the data and how to turn it into something meaningful. And I see some questions already from Ram asking, can I show the project GitHub repo, the setup, etc., etc.? Yes, stay tuned, because that's basically the whole point of the presentation, showing you the code, but showing you that it's effectively on GitHub as well. Like, if you can already Google it, probably. But yeah, so I don't know, where should I start? Like, I feel like I should maybe show you a quick demo so that you guys stay entertained and walk through the whole thing, and then we will dive into how things work, and probably starting with the gas sensor proper. So this is me. This is my my setup. So that is an M5 stack Core 2 from M5 stack. Pretty nice ESP32 based, battery powered, actually. I think the red thing is a battery. And it is running the artificial nose code. Typically, what some people have seen is that usually I go the sort of the extra mile to have the whole thing running in like a super shiny 3D enclosure, where you have the sensors actually somewhere within the nostrils. Here, the original device I was using was the Wio terminal. So this one is actually ARM-based. It can also run the new version of the code that I have now ported to Zephyr. But yeah, let's look at, say, this one. So there is some kind of graphical user interface. It's pretty basic, but we will actually see how I mean, it's also basic code-wise. Like, I really didn't have to do much to trying to make sure that the autofocus is right. But yeah, there seems to be some gouges, and there's actually more if I were to put something smelly in the jar. So I'm gonna pick up something which is effectively, and that's the sensor. The sensor is right here, and we'll talk about how it works. But let's put the sensor in the jar, and let's have a look at what's going on here. Well, it's already reacting, actually, and I hope, please autofocus, get it right. There we go.
There you go. You got it.
And so there's, well, in total, there's actually 4 lines, 4 things that are being put on the chart. And then there's the gouge that reacts to, it's basically something between 0 and 100%, which gives you like with what level of confidence the nose is smelling what. And so right now it's pretty certain that it's lemon, and yes, it is. Like, I'm not cheating. Like, I've actually retrained the whole thing just yesterday, and this says citron, lemon. So that's essentially lemon essential oils. So that's kind of for the really quick demo. Eric is actually putting a link to the artificial nose GitHub repo, the original one. Yes,
and if you further down, he's got the new one too.
Exactly. Like, if you, oh, okay, perfect. But yes, exactly. So that's the this has been around for many years. Now the full Zephyr port would be available at a similar URL, except that you would add -Zephyr at the end. So yeah, so that's for the demo. I think we said that maybe it could be useful to dive a bit into how the sensor actually works. Because one thing that I typically like to, I think many of us in sort of this industry, or whether it's just a hobby for you, IoT, Arduinos, embedded development, we're all familiar with, temperature sensors, humidity sensors. There's actually many sorts of sensors, and that's something that I think we should really have sort of like top of mind, because when you realize that pretty much every physical thing and physical quantity out there can be measured and turned into an electric signal and fed into a computer, then you can start thinking and approaching things differently. And so it turns out that for smelling and measuring smelly things, there's many ways to do it, but one is using, and I'm no chemist, I'm no electrochemist, but I understand just enough about it. So the sensor that you saw before, it's effectively a 4-in-1 sensor, and the 4 squares are 4 tiny slices, tiny pieces of a particular metal oxide semiconductor. Depending on what metal that is, it will react to some chemical compounds contained in the air. And so the way it usually works is that you heat up the sensor quite a bit, and then there's basically an oxidation reduction, a redox reaction happening with the molecules of whatever compound this piece of metal is meant to interact with. And some electrons are moving around, and that causes a change in resistance of the sensor. And that's typically something that you would get to measure in your microcontroller, right? You would be feeding the data, and depending on the data sheet and whatever, however your sensor is supposed to work, maybe 10 ppm of volatile organic compound will register as 100 ohm, and maybe one order of magnitude more will be double the resistance or whatever. And so that's basically sort of the starting point, right? And of course, like many other form of sensors would more or less work the same, right? Like a thermistor or like whatever. And this data, yes, you had a question, Kate, or?
Yeah. So
Yes.
I may be jumping ahead on you, but what are those for? What are the 4?
Yeah, that's this one is actually really interesting. So that's by the way, like sort of spoiler alert and disclaimer, this is a really basic sensor, as in I'm sure there are industrial grade sensors that are way more sensitive, way more that are actually calibrated, which this one is totally not. Okay. If you were to order this sensor off the internet and try and use my the model I trained, it might not work because it's just not calibrated. But the four quantities are one is volatile organic compound, sort of like the general definition of a volatile organic compound, and it would tell you how many ppms, or like how much
parts per million.
How many parts per million? Yep. Then you would have CO, carbon monoxide. You would have NO2, nitrogen dioxide, and you would have ethanol. And the thing is that with those 4, and this is where sort of the AI does a lot of the magic. You would think, or I'm no cook, like professional cook or professional like chemist in the context of food, etc. But I would expect something like sourdough starter to contain and to emit not only carbon monoxide, but potentially carbon dioxide as well. I don't have a sensor for carbon dioxide, but that's fine, because it turns out that the CO sensor kind of reacts to CO2 as well. And it turns out the volatile organic compound sensor as well. No one knows exactly how, to what extent the 4 sensors end up picking up other molecules, but they do. And this is where you can get the AI to sort of learn those patterns that might be well hidden in the sort of sensitivity curve, etc., of the sensors, and you would not be able to sort of figure that out just by reading the data sheet.
So Ram's asking, how often did you observe false positives in this model in the sensors?
Yeah, that's actually a really good question. So the first caveat is getting like this thing out of the way, which is the sensor itself is not like the most accurate there is. So part of the false positives might be just that. Sometimes like it takes time for the sensor to actually react. Like if you smell something really, really strong, it might take maybe a few minutes until it's all cleared up and ready to smell something else. And it also, due to the lack of sensitivity and also like the resolution, like the actual accuracy of the sensor, it might not be able to make up the difference between a few things that are really, really, really close. So you can work around some of that by tuning the AI model, and or like if that's not enough, then maybe a better sensor would be needed. Or something that I tend to really stress is that we tend, and I guess I myself first, we tend to do a lot of anthropomorphism when it comes to building smart devices, but there's nothing that forces you to build a nose that only has gas sensors as the input, right? Like you can sort of complement and help work around some limitations in the sensor or in your design by just adding more data sources. And maybe if you want to make up the difference between water, wine, and orange juice, sure, maybe a sensor would be able to pick up whatever scent comes from them, or you just use a color sensor, and they'll do the same-ish. I mean, if what you care about is figuring out the difference and not really smelling, that might be what you need, right? So.
It depends if your wine's a rosé that has an orange tinge or not, I guess. But then it's also density and a bunch of things. We actually have another question from Hybrid Robotics: is what sensor is it that you've got here?
So specifically, the sensor, this one is from Seed Studio. It's called the Groove. You might be familiar with the white connector that makes it super straightforward to connect to your Arduino shields and whatnot. A Groove multi-channel V2 gas sensor. You can get it, last time we checked, it's something like €30, $30. It's actually not cheap. There are a few others that I've been playing with that actually work, if not better, actually, than this one. Bosch has the BME 288 off the top of my head, which I believe you can get for like four or €5. But that's actually an interesting segue into some of the things that porting this original design to Zephyr is bringing. In that, just like looking back a few years back, it was a weekend early in the pandemic. I had this let's improve the bread recipe thingy, and I had an Arduino lying around, and I ended up in just a few hours writing, a few hundreds. Ended up being a couple thousands, I think, lines of really crappy, frankly, Arduino code. And some of you might be familiar with the Arduino ecosystem. It's awesome. Like you have, and I would do it the same way, just to be clear, if I were to start again. You have this crazy ecosystem of like hundreds of drivers that are available in libraries. And there was a driver for the gas sensor that was out there. There was integration with the AI framework that I ended up using, etc., etc. But the code, like the nature of the Arduino framework, is that it sort of guides you towards, you're going to put everything into this super loop, and you're going to do everything there, and you're just sort of organically, you will tend to write boilerplate code, or maybe it's just because I suck at writing embedded code. But the thing is, for something like the artificial nose, the way it works, and I can actually pull, and yes, to the person, to Hybrid Robotics asking about BME 688, I believe that I said 288, but I think I meant 668. If that's the one that came out like a year or two ago with actually built-in AI, then that's the one. In terms of, let's see, skipping ahead. Yes, there's a lot that the artificial nose does. And most of the code in the original, like the one you actually see on the picture, the Wio terminal-based artificial nose does a lot. Like there's, of course, hardware interaction to get data from the sensor, to control a fan, possibly if you have like the full the enclosure and stuff, you want to run. Eventually, I turned it into an yes. Go ahead.
No, I just say you want to suck up the air. And
Yes, which actually is a really bad idea because I couldn't find a fan that's slow and gentle enough so that it would only like create a small breathe as opposed to like sucking the air really, really fast and not leaving the sensor any time to actually process yeah. It's so I'm no chemist and I'm no like fluid dynamics expert or whatever. So I'm sure someone could come up with a better way. But usually when I do the demos, I actually just take the sensor off the...
Just do something. Start something. That's the key.
Yes. But so yeah, the artificial nose does really a lot of things. And if I can actually pull up a different screen, hopefully I'm still sharing on the other laptop. Let's see. There's going to be lots of multitasking.
Yeah, Ben's got a question about the data sets, but we'll probably get to that a little bit later on, I think, right?
Yeah, sure. Or maybe, yeah, but actually, that's an interesting one. And we were chatting about it yesterday, Kate. The fact that obviously there's tons of data sets available for like training computer vision models because it's mostly non-controversial and well-determined how you would, like if there is a cat on a picture, then someone, like some human can go about and label the data and say, oh yeah, this is a cat. And then you have some data set that then can be fed into some training frameworks. For smells, it's kind of hard because like, how do you name the smells? Like what's the sort of the ontology? And do you name like the smells as in vanilla, citrus, orange, etc.? Do you try and more categorize in terms of like the actual chemical compounds with like the funny scientific names?
You know, your first picture has a glass of wine and the breadstick there. There's actually a full wheel of how to classify the smell of wine. That would be one framework, at least. It might be startable, but I suspect there's others out there too that we could be playing with. But I guess it's a question of, you know, which frameworks would people want to agree on for creating this type of database?
Yep. Yes, but yeah, like I would love for such a sort of open source data set to exist, but I haven't. Yeah, I couldn't come across one. Yeah, quickly, the Arduino code base, just to show you that it is indeed terrible. And one thing that really made me want to rewrite it for many years is that this artificial nose thing, it's been around for several years, and it's inspired lots of people because I made the point early on during the talk to talk about like the gas sensor and the fact that many of us didn't or don't necessarily realize that gas sensor exists in the first place. And so when I started like a few years back to build this proof of concept, put this proof of concept together, many people, including people from the perfume industry, the agro industry, etc., they reached out to me and they were like, we want to buy this. Like, this is awesome. And I was like, really? Like, you guys don't know? Like, I mean, gas sensors are not new. AI, to some extent, is not new either. But just sort of realizing that just the two of them can actually work together and achieve really great things. Many people didn't realize that. So one thing that the project has done and helped is that being open source, many people, including like really young kids, ended up taking inspiration from it. And then I felt bad because the code is really terrible again, and not really easy to maintain, not really easy to, like, if you want to tweak the UI, if you want to tweak anything really, it's just really complex. And more importantly, one thing that the legacy version of the code was really using lots of bad practices and bad patterns is that everything happening in a so-called super loop, what that meant essentially is that you could get in a situation where, initially I realized, okay, training my model and turning raw sensor data into actual smell inference, it's going to be a matter of, and I have a slide for that, which I should, yeah, it's going to be a matter of smelling, capturing data over a few seconds. Like you're actually looking at the real data here. 15 data points acquired every 100 milliseconds. So you have 1.5 seconds worth of raw sensor data, which obviously you need to acquire at a pretty specific rate because, like, I mean, this is sort of the fingerprint of the smell, right? So keep that in mind. It needs to be fairly accurate, the sampling rate. And then this raw data, you're going to feed it into an algorithm that's going to try and extract some patterns. And intuitively, with my human brain, like when I was looking at this data, I was like, okay, if I were to write the algorithm by hand, I would probably try and look at things like, hey, it looks like, so let's say this is, I don't know, this is when you're smelling whiskey. It looks like all the sensor readings are going up. So my algorithm would need to extract this information. If it goes up, it might be whiskey. If carbon monoxide fluctuates quite a bit, whereas volatile organic compounds goes up steadily, then that might be something else. That might be some other key marker. Except that obviously I didn't want to try and come up with all those things by hand. So that's where the AI kicks in and does some like signal processing and turns this raw data into like goes through a very basic signal processing block that will extract the things that I just mentioned. Basically, is the data going up or down? Does it have a lot of variance or not? What's the minimum, the maximum, standard deviation, whatever? Those key markers are what's then fed into the neural network so that you can correlate those markers with the smells that you're expected to find out. Quick question from Oliver and quick answer from my side. Yes, on my other laptop, I'm showing VS Code running on the Mac. But there's, I'm going to actually probably jump between two computers because I have also some, yeah, we'll see, whatever I have time to cover. And this is where, this is a reminder, oh, Violet, really great to have you as well. Reminder that please just shoot all your questions and Katie's actually helping me make sure that we're seeing them too.
Yeah. So one that's not come up yet is how long did it take to port it over to Zephyr? And what was that like?
So I think, yeah, Kate, you mentioned that this talk actually I gave, or this presentation, well, I gave many times in the past, but in this particular form, I think it was about a month ago, there was a conference where a few months back, I had made a proposal, which would be, hey guys, I'm going to give a talk on how I migrated my hackish artificial nose running on Arduino and lots of boilerplate code, how I migrated it to Zephyr. Except that I didn't get to work on the actual presentation until I basically boarded my plane to Raleigh, North Carolina. So most of the rewrite, well, of course, there are some pieces that I just, like some code that I ended up not completely rewriting, but the actual infrastructure of like porting everything to Zephyr so that it's really properly multitasking and using like graphical user interface and whatnot. It was whatever time it took me to fly from Paris to Raleigh, and then a few additional hours in my hotel room. But seriously, that's how fast it went. So, and I know my way around Arduino embedded development and Zephyr, but I'm by no means like a professional embedded developer. So yeah, kind of like it was pretty quick. And let's try and dive into the code. First, like this is how it looks like before. Again, this sort of Arduino mega loop. This functionality though is something that I would still need to have even if I were to run on Zephyr, right? Like at some point I need to acquire the sensor data. When I have the raw sensor data, like a couple seconds worth of raw sensor readings, then it gets fed into the AI model. And then at some point I need to get to be aware of potentially like hardware interaction, someone pressing buttons, whatever, refreshing the GUI, pushing data to an IoT server, because we're going to actually see that the nose is actually also sending data to the cloud. Looking at the Arduino version, this might sort of ring a bell for some of you, but I said that the model expects the data to be raw gas sensor readings acquired exactly at 10 hertz, like exactly every 100 millisecond. I need a reading. Except that if I do everything in a loop, what if running the AI inference takes 50 milliseconds and then refreshing the GUI takes 30? Well, I guess that's fine, as long as I know that those are sort of bounded, and frankly, they are. But then sending data to the cloud, that one, if it's really happening synchronously, we will have a problem, and it might not show like directly. It might only be the UI becoming slightly unresponsive. But one thing that will actually happen is that the AI will start giving readings that are wrong, and you will have no way to know why they are wrong in the first place. Or, I mean, there are ways we could talk about it, but that's that could actually be problematic, right? So that's sort of why that's basically the main reason why I migrated everything to Zephyr, frankly.
Okay. Do you want to go into the code, or do you want a question right now?
Yeah, let's take a question if there is.
Sure, there. So Hybrid Robotics is asking, I'm going to get, there you go. You've got it up now.
Mm-hmm.
Could they be put in some sort of fusion algorithm and fed into a model, do you think?
So I'm not familiar with the Mix 68814, but I'm assuming this either another gas sensor and or to my point earlier, something like maybe a color sensor, light sensor. Yes, typically you could definitely do some fusion and feed everything to a model. I'm actually going to, before diving into the code, let's make this really interactive, and let's just show really briefly the way I trained the data. And this is by no means a plug to Edge Impulse, but just briefly showing you sort of like the main aspect of how the training works. Typically, with this web interface, like you can really easily forward raw data that you acquire from whatever device you have attached to your laptop over USB, or whatever data source that you have as CSV. Let's say you've already captured minutes and minutes of raw sensor readings. You've already labeled the data. And so and actually you can see that I effectively did that yesterday. So this is 1 minute something of smelling lemon. This is 1 minute and 30 of smelling ambient air. And you can already see some differences, right? Like here, nitrogen dioxide would be in the 500s and everything else is really, really low. Whereas for lemon, this is completely different, right? And there's probably anything in between where it's like going from from ambient air to lemon. Mm-hmm. To me, that's also something that I labeled lemon. And this is where like lots of the fusion, right from, I mean, if you're familiar with Keras and like Python, like Jupyter notebooks, etc., you could create and train a model out of the raw data yourself, or using Edge Impulse, like essentially it does all the magic for you. You're like, okay, what if I were to look at the raw data and extract only like 4-second slices, and then go through the signal processing block, which is effectively turning the raw data into average, minimum, maximum, etc., which means that you would end up with some features that you extract, and you get actually able to figure out if those features are meaningful, and if you're confident that your signal processing block is extracting features that allow somehow to map each label and each data point properly, then this can probably be fed into a neural network that's going to be trained. And as you actually see, you get actually a really good result with only minutes of training data. I mean, eventually, I think there's, and we were seeing that earlier, Yeah, I smelled 20, let's see, how much is that? Yeah, 20 minutes of ambient air. It's not that much, and I could do with less actually, but I was trying to make sure that it was representative of all the variances. If you have to answer hybrid robotics, if you want to feed more than just the data from the seed sensor, and you want to add BME 688, etc., this will be just more data that you have in your rows, and sure, that will work. And again, it doesn't have to be only gas sensor data. It can be anything else. Like if you want to feed the weather forecast because you think that the humidity in the air may have an impact, that wouldn't be a bad idea. If it doesn't have an impact, that's fine, because your neural network will just sort of ignore the characteristic if it doesn't accrue to the result that you're expecting. Right? The code. Should we move to the code eventually? Yeah, so that was so that's the Arduino code. That's the Zephyr code. Essentially, there are moving away from the mega loop or the super loop. So everything is on GitHub, like I mentioned, right? So feel free to check it out. There's actually lots of I've taken lots of inspiration from the Zephyr official example application in terms of trying to make this application a good citizen in terms of structuring the code base properly, integrating with GitHub Actions so that you have like you can actually run continuous integration of the project, etc. But yeah, looking at a few things that the code does, and some of the features that I actually leveraged and that make, in my opinion at least, make for something way more portable and way more maintainable than the Arduino code was. Well, it starts with the main, right? The main thread is effectively not a thread, if you will, because it's just creating all the different tasks that I want to have in the system. And that's really something that I want in the context of doing TinyML. Like we said, sensor acquisition needs to be its own island, and it needs to be something that runs with a fairly high priority so that exactly every 100 milliseconds we get to acquire sensor data. And the thing is, well, one, this is good that I'm able to leverage like an actual like threading mechanism so that it runs properly in its own task. But one thing that's also really cool is that I can easily leverage the Zephyr sensor and driver model so that I have a real abstraction of the what my gas sensor is. And again, to hybrid robotics point, I mean, this could be helpful in your case. It doesn't really matter at the end of the day what actual sensor you use, as long as there is a driver in Zephyr, or you might need to write one if it doesn't exist. But it will eventually, what matters is that it will end up exposing data in a sort of standard way, in that here it doesn't say seed gas sensor, right? It's just like I'm retrieving from my Zephyr device tree something that is a gas sensor, and I will query channels on it. But if I'm looking at another type of sensor that also has NO2, CO, whatever, then I mean the code wouldn't change all that much. Actually, one thing that the code does too, and there would be other ways to do that, including leveraging the built-in emulation framework in Zephyr. But for me, like the quick way to get simulated data in case there's no sensor actually connected, that would be one way to look at it, right? If there's no gas sensor found in the device tree, then I would just like simulate data. And so what this task does is really just that: every 100 millisecond getting sensor data and then putting it into a ring buffer, because we saw before, right, that there's a slice of a couple seconds of data which we care about, and we sort of like keep feeding this buffer, removing old samples as they come. And so, yeah, we put the data in a ring buffer for others in the system to potentially consume. And that's exactly what the inference task does. another thread, which is basically where we run the inference. And here, most of what this task does is effectively calling TensorFlow Lite and calling the code that you can get automatically right from the Edge Impulse Studio. So it effectively gives you a zip file with your actual TensorFlow Lite model, and also all the libraries and all the APIs that you might need to feed your own raw data into that model that you just trained. And so this task, so another task in the system, this one with not as high of a priority as the sensor reading, because I mean, I care about smelling things, but if it takes longer, or if I don't have time to properly compute all the inferences, it shouldn't be all that bad. What really matters is that sensor acquisition is accurate. But yeah, in an infinite loop, but in a dedicated task, this would effectively get data from the ring buffer, granted that the ring buffer has enough and that the code has been running for long enough. And then it just feeds the data into Edge Impulse. And frankly, that's it. And so you feed the raw data into Edge Impulse, and you end up with a result that will give you with like what it is that the model thinks it is that you're smelling, and with what level of confidence. And that information, I might need it somewhere else in my system. I might need it, or like anyone really in my in the system could use this information. And rather than using raw primitives in Zephyr, like queues or like really basic primitives, I figured that this kind of information is like, it's business data, you could call it, right? Like the what is the inference is sort of a first-class citizen in my application, which the UI might decide to display on the screen, or which I might decide to store it on the file system, or to push to a server using MQTT or whatever. And so this sort of like business data, it turns out that I turned it into, I use Zbus to effectively move it around. There might be several consumers, several subscribers in the system, like again, the GUI, the file system, whatever, that might be interested in consuming the data asynchronously, probably. And so, yes, Kate?
So, okay, so we've basically got GUIs, and we started talking about GUIs. So this is our like, okay, you used LVGL, yes. You were talking about what's it like using that on top of this?
Yeah. So, and this is where it's super important to decouple things. And so, whenever a new inference result is available, that is a label, a level of confidence, and a few other things, then that's something that might be consumed and displayed in another and handled by yet another thread, which this time around will be the GUI thread. And one thing that I used, and that works just out of the box in Zephyr, is LVGL, so the graphical user interface framework, where essentially, like, as opposed to previously in the Arduino, where most of the graphical interface would be sort of manually written by hand, like pixels displayed on the screen. It's fun until it isn't, right? You really want an actual framework. And that's what I'm doing with the LVGL. And briefly glancing at the code, the way it works is that it would subscribe to Zbus to know whenever a new inference result is available. And it's really like pretty straightforward. You would probably do the same in like Java or JavaScript, or like super high level languages where you want to consume data out of a bus. And so data here would be the message that I get is an inference result. And I use it to refresh my screen, right? And to display things on the screen. And creating the GUI would be something that I've done here, where I would create a chart. If the screen is large enough, I would create the gauge that we saw as well, but on a really small screen, like switching really briefly to another device that I have right here. Let's see, let's put it really big on the screen. This is the same application, same sensor, except that this is running on another super small ESP32 based device. Same code that we were seeing just here, except that when I'm using the small M5 stack Atom S3, the screen as per information in my device tree. The screen has a resolution or an X resolution of less than 240 pixels, which means that it probably doesn't make sense to draw this. It probably doesn't make sense to even have that as part of my firmware. So it's completely compiled out if the screen is too small. And then I create a label. And said label is the one that would be automatically updated in the whenever new data is available on my Zbus channel. And so that's one data consumer, and another one would be using. I mean, this is an IoT device eventually. Like originally, it was just a hack for looking at like a sourdough starter and whatnot, but effectively there's actually like real use cases for this kind of device. Like think about putting and I should put myself back on camera probably. Think about putting such a device in an office building, and you're the company responsible for looking after for doing the cleaning essentially, and you don't want to send someone every day or like twice a day to clean restrooms or any room really that doesn't really require cleaning. And for restrooms, it might be that you can actually smell whether the air is like, if it smells good enough, then it might be an indication that you might not want to send someone. If you couple that with a people counter sensor, and if you know for a fact that only 3 people use the restrooms and that it smells okay, then that's fine. Except that as soon as the sensor is like put right into the ceiling of this particular room, then it's not like, I mean, it needs to be connected somehow. It's not like someone is going to go and like check what is displayed on the screen, and it wouldn't make sense anyways, because if you're already checking the screen, you might as well clean the room because you're there, right? So next thing I did, I guess, is add MQTT to the mix. I want to enable things like if my device tells that it's smelling bad, I want to be able to send the data to the cloud so that I can sort of navigate my IT infrastructure and be like, oh yeah, the particular device knows TBR26P whatever. This particular device indicated that it's smelling bad. As per my information system, that means that I need to send a notification to whoever to ask them to go and look after such or such room. And so code-wise, and mostly demo-wise, actually, what that means is that there is another Zbus consumer in my
system.
Another thread and another task that's going to be notified when data is available, and when there is a new inference. So when we smell something new, it's gonna publish data to the cloud using the MQTT protocol. And MQTT, so for those who don't know or not familiar, is sort of a publish-subscribe mechanism where you have a central, like a server, similar to Zbus to some extent, except that this would be running on the cloud. And you have a server, and you have a topic hierarchy where all your devices will be able to post data. And actually, in my case, it would probably be wiser if I were to do something like this, like sending to something that's really namespaced. But yeah, the idea is that this code will be publishing whenever there's new inference. This will be publishing into the cloud. And let's actually see it in action. So for that, I'm going to do a few things. I'm going to do like switch back to camera. So we're gonna keep looking at the sort of the one I was demoing first. I'm gonna plug it. All right, I've used USB to plug it to my computer. The thing is that I want to actually configure it so that it effectively connects to Wi-Fi. Like, let's see.
So you're using the shell here?
Yes, I'm going to connect to the Zephyr shell. So let's see, it might, yeah, for some reason, it sometimes need, I think it's actually my USB cable that's acting up. All right, rebooting. There we go. All right. So right now I'm connected to the artificial nose. Why is it not starting up?
Because it's a demo, of course.
Yes, of course. It's because it's a demo. That's really weird, actually. Well, we will switch to the other one, the tiny one, if this one decides that it wants to act up. Okay, yeah, I think it was a badly plugged sensor or whatever. This is the Zephyr shell, which I love. And for those who don't know or don't use the shell, you should. You can do many things from the Zephyr shell. You can interact with, I mean, depending on what you enable. Like when you go production, you probably remove the shell altogether. But for prototyping, you can do things like getting data from the gas sensor and get some readings from the gas sensor. You can do many things like get infos regarding the threads. With that, I think it's kernel threads. Is it? Yes. Get information regarding all the threads that are running, etc., etc. One thing, Machias is asking what version of Zephyr.
Okay.
Yep. Well, let's see. Let's ask the shell. Help. I think we can probably get that information from device, maybe. No. I'm sure there is a shell command for that. Well, there was actually, kernel version. So we are running off of 3.5 of head, pretty much of the Zephyr main. But there's nothing in what I'm demoing that wouldn't run on past versions, except maybe what I'm going to show right now. Some of the particularities of the Wi-Fi integration might, some of them are new. But yeah, what I want to do essentially is use the Wi-Fi shell to connect to the internet, because right now I'm not connected. I have enabled the MQTT capability in my nose, but it needs to be connected to the Wi-Fi. And so for that, I will connect to my home Wi-Fi. So I might go off screen just briefly, just when I'm going to share, copy paste my Wi-Fi password. So let's go off screen really briefly, but I'll be right back as soon as it's off screen. All right, and we're back. So I issued a command to ask I issued essentially Wi-Fi connect with my SSID and my password, and now the device is connected. We could probably look into other Wi-Fi commands to see where we're at in terms of are we effectively connected. I think there's Wi-Fi status. Yeah, there is. So I'm effectively connected to my home router with reasonably good, not so good actually, connection, etc. And I'm sending data to the cloud. I'm sending data to a public MQTT broker, Hive MQTT broker. Kate, are you ready to be on screen? Because you're going to help me with the demo here. Like you're all the way in Austin,
right?
And you're going to use a web, the HiveMQ web interface to connect to the broker.
Okay, I'm going now.
Yeah. Yes. And now you can so that will be on the subscriptions side. as per my code before, yeah, exactly. So you would, if you subscribe to smell/wildcard, essentially, you should see data coming in. And let's see if the demo, I think the demo works. Switching back to my camera. So we're here, we are actually showing, let's see, let's put it that way for now. So this is smelling ambient, yep. But if I were to put my lemon thing, or should I do time this time? I will do time.
Oh, because we only have a few minutes left, so time seems like appropriate.
I realized that, but that's pretty much a wrap after that, I think. Let's see. Oh, it says lemon, but it should be time actually. So let's see. It might take a while. One thing that I didn't mention, some of you might have caught, it was mentioning at some point somewhere in the code, anomaly detection. One thing that typically the model, yeah, interesting. It's saying lemon, I'm pretty sure. Yeah, whatever. This is one of those corner cases.
But
time's coming.
It's showing time now. I figured it out now. Yep.
We are running out of time, right? Yeah, one thing that we could actually surface in the code, in the UI, is something that the AI model, an information that it gives, and it's actually really important, is there is, in addition to the neural network, there is another model that can be trained, which is anomaly detection, which basically can help us figure out whenever there is a reading whenever the data that you feed into the model doesn't seem to look very much like the kind of data the model has seen during the training, it might be a sign that whatever inference you will get out of your model might be to be taken with a huge grain of salt. So we could have that taken into account as well. But yeah, that's I think that's for the demo really. There's many other things that you will see in the repo if you check it out, like the ability, for example, to run natively on the desktop. Like if you don't have something like the Wii or terminal or a device with the GUI handy, you can still run LVGL right on your desktop, right? That's definitely a possibility. I think I have the demo for that. Maybe I can briefly put it on screen before we run out of time. But let's see if I put this guy on the screen, right? Like this is running same UI, slightly larger actually, because we see that the graph has like those tiny little dots that you wouldn't get with the smaller version. And you have the simulated data that we were seeing earlier, because on my desktop, I don't have a real gas sensor. So it's using the branch of the code that simulates data, but it still goes through the AI model. It still has the GUI displayed. So that's something that you can do. Like if you check out the code, you will have access to that as well. And with that, we are nearing the end. Did you have more questions, Kate, or was there anyone from the audience that we didn't?
Well, so the question is sort of one. This is the last one. The data sets in the community, and that was one of the ones I was going to ask. Is if people are interested, how do we start contributing to creating some of these data sets? Any thoughts here, or how do we start that?
So a starting point is definitely like checking out the repo. But in terms of building the data set, I think I don't have the link handy, but I would like to say last summer, as in like over a year ago, Google Research, they published a paper where I think they've started to put out there some public data sets of molecules, like actual molecules, and how they smell like in a sort of an objective manner. So I look up the link and put it in the comments on YouTube so that you can do some reading. But yeah, that's And Luke, answering that question, like hours, like, and it's not like a sort of marketing pen, or it's really like, yeah, I did that basically on a plane on my way to a conference, please check out the repo. I'm sure there are, just like back in the Arduino days, there were some ugly patterns in there. I'm sure there are in the new Zephyr repo, but please just like open issues and let me know if you see anything that could be improved. Yes, and Ram, I will make sure to put the link out there. And with that, I think we are nearing the top of the hour.
A little past.
This was great. We will be back in 2 weeks' time. I don't have the chart handy, but this will be with Keith Packard from the Pico libc project, and he's going to talk about everything tiny C libraries for microcontrollers, and I'm actually really looking forward to this one. Yeah, that's it. Any last words, Kate?
No, thank you. Oh, actually, one last question. So, do you ever use this for figuring out if you can make bread properly yet?
No, that's where I'm. Part of the reason is that it actually takes a lot of time to create the data set, because I would need to bake dozens and dozens of baguettes, label them as in, oh, they're good, they're not so good, they're all soggy, whatever. So yeah, no, I did not. And with that, I think we're already past the hour. So thanks everyone. Thanks, Kate, for the help with co-hosting this one, and we'll be back in 2 weeks. Bye.
Thank you.